Oh, that's next week. Here, let me make that clear. So there's no lab the day of the test.
Oh, that's the chapter 1 though.
1 and 2.
Oh, 1 and.
So, government announcements. The second chapter 2 homework is due on Wednesday this week, the 12th. The first chapter 3 homework will be due on Wednesday next week, the 19th. Chapter 1 and 2 review will be on Wednesday the 12th in the SI session. You'll also have the chapter 2 quiz on that day. Forgot to put that up, but that'll also be the chapter 2 quiz. The chapter 1 and 2 exam will be on Monday, the 17th. That's a week from today. In lecture, you get 1 sheet of notes as a formula sheet. You'll need a calculator. I will have calculators to loan out. And we won't have a lab that Monday. If you need to make up any labs, you can make up labs that day. We will have a lab today. I guess I can put that in. Lab today. We do have a lab today. It is next week that we don't have. Any questions about this? Like your quizzes, you get 1 sheet of notes. He uses a formula sheet. Okay. So, just a reminder of what's coming up. I will put up an announcement about the exam after class today. So we're starting chapter 3. We finished chapter 2. You'll have the quiz on it on Wednesday. We're starting chapter 2 was about describing how motion occurred. What's known as kinematics. This is moving on to describing why that motion occurred, or what's known as dynamics or kinetics. This is about force and motion. We're going to talk about how force is related to motion and how force causes changes in motion. So, force and motion is about cause and effect. Force causes motion or change in motion. In chapter 2, we studied motion, but not the cause of the motion. In this chapter, we're going to look at both the cause and the effect. We're going to look at Newton's laws, Newton's 3 laws of motion, which describe how force and motion are interrelated. Newton's law of universal gravitation, which describes the more general, we describe gravity as there's this constant acceleration on Earth, but the more general rule for gravity between any 2 objects is Newton's law of universal gravitation. Name? So we'll look at that, and we'll also look at the concepts of buoyancy and momentum. So buoyancy is about how things float, and momentum is another way to understand the inertia, the persistence of motion. So Sir Isaac Newton, really smart guy, also kind of strange. He lived from 1642 to 1727, and he was only 25 years old when he formulated most of his discoveries in math and physics. What happened was he was studying at university, and then there was a plague, and so he left the busy university town and went more or less out to the country and made a bunch of progress on his ideas then, when he had time to think, because he didn't have to do anything because everybody had left because of the plague. And so his book, Mathematicals of But then he sat on these ideas for a very long time before he published his big book. So there was a big debate about various things because among the things he figured out was calculus, invented calculus. And Leibniz also invented calculus around the same time. And so there was this big nasty fight about who did it first. So his book, Mathematical Principles of Natural Philosophy, is considered to be the most important publication in the history of physics, because he basically put forward the beginning of many fields of physics. So not just like the basics for all of motion, and how force and motion are related, but he also did he did a detailed study of optics and several other things. He kind of built up a baseline for much of physics. Now, force is pushing or pulling on something. It's a vector quantity capable of producing motion or a change in motion. It's a push or a pull. And you experience force all the time. You know, when you push or pull on anything or any movement you do in your body has got forces involved. So a force is capable of changing an object's velocity and therefore producing acceleration. And a given force may not actually produce a change in motion because other forces may serve to balance or cancel out the effect of that force. So if I'm standing still right here, your name? What? Okay. So if I'm standing still right here, currently, gravity is applying a force pulling me down, but the floor is applying a force in the opposite direction, pushing me up. They're equal in size, they're canceling each other out. At the moment, I don't really have any side-to-side forces, but like that's an example. So the unit for force is the Newton, named after Isaac Newton. 1 Newton is 1 kilogram meter per second squared. 1 Newton is 1 kilogram meter per second squared. So now we've gotten to the point where, name? We've started to get units that are annoying enough and complicated enough that we define them, we give them names. So a kilogram meter per second squared, you don't want to write that. So we gave it a name, called it a Newton. And subsequent units that we'll cover in later chapters will also have names. Now, here's an example of balanced and equal forces leading to no motion. You have 2 teams in a tug of war. They're applying equal forces in opposite directions. Those forces are going to cancel out. They're not going to move. They're equal in magnitude, but opposite in direction. Basically, when you add those forces up, they add up to 0. So one of the helpful things, there's in fact a whole field of study called statics that's built around this idea that if things aren't moving, all the forces have to add up to 0. And you can literally take a course on solving problems just like that. It's an engineering thing. Now here, we have unbalanced forces. Force 2 to the right here is bigger than force 1 to the left. So there is a net force, a total force. So net just means total. The total force is to the right. Your right. So the net force is to the right. So this thing will accelerate to the right. There'll be motion to the right. So here's a question about that. If a block experiences a 2 Newton force to the north and a 3 Newton force to the south, what's the net total force on the block? 2 Newtons north, 3 Newtons south.
1 Newton south, right?
Yeah, it's 1 Newton south. So the net force is just the sum of the forces. So 2 newtons north plus -3 newtons south. South is, we'll treat north as positive, south as negative. Gives you -1 Newton, which is 1 Newton to the south. And as usual, these slides are up on Blackboard and will be posted with the recording. Here, we have a block experiences a 4 Newton force to the north and a 4 Newton force to the south. What's the net force on the block? 0. These forces cancel out. So 4 newtons plus -4 newtons equals 0 newtons. The net force is 0. And you don't need to put down the direction for 0, because it doesn't have any magnitude, so the direction is meaningless. And then here is a little more complicated. We have a block that experiences a 2 Newton force to the north, a 3 Newton force to the west, and a 3 Newton force to the east. What is the net force on the block? Here is a diagram. Yep, this will be 2 newtons to the north. The east and west forces will cancel each other out, and you'll have just the north force remaining. So these are vectors. You can add them up component-wise. You can treat north and south separate from east and west. But it's 2 newtons north plus 3 newtons east plus 3 newtons west. Those cancel out, and you're left with 2 newtons north. And that sort of thing will happen pretty often. So like if you have a car traveling down the road, horizontally, it's got some force from the engine that's driving it forward, but it also has gravity pulling it down and the road pushing it up, and those cancel out. And a lot of the time, you'll just ignore the forces that cancel out in the direction you don't care about, because you know it's not moving up or down, kind of thing. So Newton's first law of motion is about what the natural state of motion is for an object on its own, not being affected by anything. So this has to do with the fact that previous ideas about motion, and if you make an observation about like moving objects, when you take some object and you give it a push, in general, it stops. So Aristotle had this complicated thing where there was a natural state of motion for everything. And the natural state of most objects was to be at rest at some level. It got complicated based on like the nature of things, which also it was also trying to explain gravity. But the natural state of most matter is to be at rest. Galileo studied actual motion, did experiments, measured motion, and came to the conclusion that things can naturally remain in motion indefinitely. This idea that the natural state of motion is just to keep going at whatever speed you're going in a straight line. Newton formalized this and put together these ideas from Galileo into the basic idea that an object, Newton's first law of motion is that an object will remain at rest or in uniform motion in a straight line unless it's acted on by some external unbalanced force. Basically, if there's no forces or the forces all add up to 0 on an object, that object will keep going, will keep doing whatever it was doing. It'll either, if it wasn't moving, it'll stay not moving. If it was moving at a constant, it'll keep moving at a constant speed in the same direction it was moving. So the basic idea of Newton's first law is that the natural state, without any external influence from outside forces of any object, is to stay at a constant constant velocity in a specific direction. Direction doesn't change. Speed doesn't change. You just keep going in a straight line, whatever way you were going. An example of this is if you say spin a mass around on a string, and when you let go of it, it will keep going in a straight line, whatever direction it was going. Because you stopped applying a force. The basic idea is that for velocity to change, there needs to be a force. So an object will remain at rest or in uniform motion in a straight line unless it's acted on by some external unbalanced force. The balanced forces are forces that all cancel out. They have equal magnitude in opposite directions, and an external force is some force from outside the system. There has to be something from outside acting on the object. This is actually, the fact that it has to be external comes from Newton's third law, which shows that like all forces, internal force, there's a consequence of Newton's third law is that all internal forces cancel out. But so it has to be external. So here, for example, if you have a spacecraft like the Voyager probes traveling out into deep space, just keep going in a straight line because no forces will act to stop it. Amusingly, this picture is not a great choice for that because this particular spacecraft does have forces acting on it and is not traveling in a straight line. Because it's currently being affected by the gravity of the moon. That image is of a spacecraft in orbit of the moon. Here, a large rock in Yellowstone National Park stays put until some force acts on it. Otherwise, it just sits there. Doesn't move. So, inertia is this natural tendency of objects to remain in motion or at rest unless something acts on it. This is the idea that things want to keep doing what they were doing. And it was first introduced by Galileo. Basically, objects tend to maintain their state of motion and resist change. And Newton went one step further and was able to relate an object's mass to its inertia. He's able to show that the more mass an object had, the harder it was to change its motion. The greater the mass of an object, the greater its inertia. The smaller mass of an object, the smaller its inertia. The more mass of an object is, the harder it is to change its motion, the more it resists change. So here, the large man has more inertia, more force is necessary to start him swinging and also to stop him due to his greater inertia, as opposed to the little kid. The little kid is much easier to start moving and easier to stop moving. Part of why you're so much bouncier as a small child is that it's easier to get you moving around and easier to stop moving. Once you get older, you have more mass and are harder to stop moving. And so when you do stop moving, you're more likely to do damage to yourself. Another example is if you have a mass on like a sheet of paper. I'll try and demonstrate here. I have a 1 kilogram mass here on top of the paper. If I whip the paper out, the mass basically doesn't move because it has a high inertia. It tends to stay in place because of its high inertia. That's the basic idea behind, that trick where you whip a tablecloth out from underneath a table and leave everything, all your places still set. The trick there is you need to do it fast enough that you don't apply enough force to get things moving. And because of this relationship between motion and inertia, Newton's first law of motion is sometimes called the law of inertia. And you could argue that seatbelts are a tool to help correct for this law during sudden changes in speed. Basically, what seatbelts do is they keep you changing speed with the seatbelt instead of having a much more rapid and unpleasant change in speed with impact with the windshield. So most car safety things are about you're gonna go through the same change in speed when you're in an accident, but it's about spreading that out. So it's less force over more time. So here, if you have a motionless mass held up against gravity by a string, if the tension of the string is providing an upwards force of 10 newtons, what is the force provided by gravity? So this is, I have a mass hanging from a string. The string is providing an upwards force of 10 newtons. So what is the force provided by gravity? Yep. Down. So here's a quick diagram. We have 10 newtons up, some unknown amount down. But because it is not moving, we know the total force has to add up to 0. So the net force is 0. So the force of tension plus the force of gravity, 10 newtons up plus the force of gravity. Force of gravity is going to be 10 newtons down. This is how scales work. The scale measures the force it has to apply to stop gravity. This is what you get with, say, a spring scale, like this. So this scale measures the downward force, the tension, and has a dial that represents that, because it's got a spring that moves to provide that tension. So this scale kind of sucks. Well, it measures. That's how that sort of scale. The other sort of scale, the force is coming from underneath. But it also has a spring, and it's measuring how much the spring is compressed to provide that force. So here we have a rocket starting at rest in deep space. It has an acceleration of 144 meters per second squared for 20 seconds, using up all its fuel. So remember from last chapter, final velocity is initial velocity plus acceleration times time. Then 3 hours after that, what will its speed be? So once the rocket is out of fuel, it is no longer doing the action that is providing acceleration. It's not, there are no forces on the rocket after it's out of fuel. So the way this works, first we need to figure out how fast that rocket is going after 20 seconds. So after 20 seconds, we can use final velocity equals initial velocity plus acceleration times time. And we'll get final velocity is our initial velocity, 0 plus 144 meters per second squared times 20 seconds, which is 2,880 meters per second. So that's how fast it's traveling after 20 seconds. Then after 3 hours, well, after that 20 seconds is up, there's no longer any forces acting on it. So we'll keep going at the same speed in the same direction. So after seeing 3 hours, it'll still be traveling at 2,880 meters per second. That's the basic idea with Newton's first law. No forces, speed stays constant, velocity stays constant. So here, we have a frictionless block, slides down a 3-meter hill, achieving a speed of 29.4 meters per second when it reaches flat ground. Along the flat ground, how long does it take to travel a distance of 441 meters? You can assume that ground is also frictionless. And velocity is distance. So distance is velocity times time. As it travels along the flat ground, the ground is frictionless, and the vertical forces will cancel each other out. Gravity pulling the block down and the force from the ground pushing the block up. So time is going to equal distance over velocity. So 441 meters over 29.4 meters per second is a time of 15 seconds. And we'll travel at a constant velocity along the flat ground. assuming there's no friction, no forces acting horizontally. Here we have a block spinning clockwise on a 1 meter string at 19.7 meters per second, and it's released with the string pointing east. How fast and what direction does the block travel? So this is a block on a string. There's my block. The block on a string and spinning it around. And it's released when the string is pointing east. And it's spinning clockwise as seen from above. So there's a picture of that. Showing the direction it's rotating. In some ways, the most helpful way to solve this is to draw it. Okay, well, here is a slightly better picture. This is the state it's in when it is released, traveling around the circle at 19.7 meters per second. When it's released, the string is pointing east, so it, at that moment, is traveling south. So its speed when it's released will be 19.7 meters per second south. And I would like to continue on and go over Newton's second law of motion. So, a bit more information about the homework. So Newton's second law of motion we talked about how inertia, more massive objects have more inertia. Newton's second law of motion formalized it, and Newton's first law of motion is what happens when there's no force. Newton's second law of motion explains what happens when there is a force. So Newton's second law of motion says acceleration is proportional to force and inversely proportional to mass. So acceleration or change in velocity produced by a force acting on an object is directly proportional to the magnitude of the force, the size of the force. The bigger the force, the bigger the acceleration. The acceleration will be in the same direction as the force. They're both vectors. They'll both be in the same direction. And it is inversely proportional to the mass of the object. The greater the mass of an object, the smaller the acceleration. So this means acceleration is force over mass, or net force is mass times acceleration. most often written this way, F equals ma. Because it's all one line. The force is mass times acceleration. So acceleration is force over mass, or mass is force over acceleration. That's a way you can measure mass. So for example, acceleration is force over mass. So our original situation, acceleration is force over mass. If we double the force, we double the acceleration. If we double the mass, but keep the force the original amount, we have the acceleration. Takes more force to move more massive objects. So force, net force equals mass times acceleration. And this is where we get kilogram meters per second squared. Kilograms is mass, meters per second squared is acceleration. So the units, force is mass times acceleration, kilogram meters per second squared. That's newtons. It's the SI unit of force. The unit of force in the imperial or US customary units is the pound. Pounds are a measure of force. And mass and acceleration are concerning the whole system, and the force here is the net force, the total force. The sum of all the forces acting on the object. And here is an example where you can think about total force on a system and the total mass of the system. So here we have two blocks connected by a string. So these two blocks are connected together. We can treat them as a single system. So we can think about the total force and the total mass of the acceleration of the whole system. So the force is applied to the blocks. We have plus 8 newtons to the right and minus 5 newtons to the left. And the mass, there's two blocks that have a mass of 1 kilogram. So the total mass is going to be 2 kilograms. So if we want to find the acceleration of the system, the total mass is 2 kilograms. The total force is 8 newtons minus 5 newtons, because we have plus 5 newtons, we have minus 5 newtons to the left and plus 8 newtons to the right. So 8 minus 5 is 3, divided by 2 is 1.5 meters per second squared. So that's how you can find the acceleration of this system. So here, if you have a 10 kilogram block on a frictionless surface and it's pushed to the left with a 200 Newton force, what is the acceleration of the block? Force equals mass times acceleration. Thus, acceleration is force divided by mass. 200 newtons divided by 10 kilograms gives us 20 meters per second squared. To the left. Here we have a 20 kilogram mass that accelerates at 28.8 meters per second squared. What's the net force on the mass? So, force equals mass times acceleration, 20 kilograms times 28.8 meters per second squared is 576 newtons. I think we can go over one more problem. So here, if a cart is pulled by a 1,440 Newton force and it accelerates at 12 meters per second squared, what is its mass? So, force is mass times acceleration. Mass is force divided by acceleration. So 1,440 newtons divided by 12 meters per second squared. Mass is 120 kilograms. And that's where I want to stop for today. We do have a lab today. As usual, come back at 3:30 for the lab. Make sure you're on time for the lab because we're going to be taking data out in the stairwell. So, like, we're not all going to spend the whole time in this room.
How did you decide it was kilogram? Like, how do we?
Because newtons are kilogram meters per second squared, and you're
Okay.
dividing by million meters per second squared.
Great, thank you.
Yeah.
Thank you.